Hi everyone, welcome to week 3, part 2 for Soil 360 at Humboldt State University. Our learning outcomes for this week have been found in a bunch of different places. In lab a little bit, and also in part 1, we looked at the decision flow chart for describing soil colors, and we talked a little bit about models, redoxomorphic features, concentrations, and pedenvoid features. I also pointed you to an NRCS resource that discusses field indicators of hydric soils. In this week 3 part 2, we're going to talk for about 15 to 20 minutes about identifying soil moisture and temperature regimes. We're also going to introduce the concept of a control section, which is very important. Some of the other learning outcomes for this week had to do with lab characterization data and micromorphological techniques. Micromorphological techniques are covered both in the Buell et al. Book, and also these two things are covered in your homework. So we're hitting a lot of these learning outcomes in different ways. But let's get on to soil moisture and temperature regimes. Before I do that, however, I would like to review the 6 categories that are used in soil taxonomy. I've taken one of the pedons that we worked with in week 2 and have put it up here on the screen for you. The series name is Amory, and that's the most specific part of soil taxonomy, even though the word is probably a place name. The family is a coarse loamy mixed superactive frigid typic Glossudelph, as written up here. The subgroup is typic Glossudelphs. The great group is Glossudelphs. The suborder is Eudelphs. And finally, the order is Alphasols. Now, the reason that I bring this up right now is that at some of these taxonomic levels, moisture and temperature regimes and particle size classes become very important. For example, if you look right here in the suborder, it has this syllable that says UD, Udic. That stands for a Udic moisture regime. Likewise, up here in the family names typically include soil temperature regimes as part of their name. So I wanted to remind you of this because what we're going to discuss today is going to come back into the soil taxonomy. Okay. I wanted to point out a resource that you may want to look up for all the gory detail of soil moisture and temperature regimes. This link points to Soil Taxonomy, which was published in 1999. This is not your keys to soil taxonomy, but a more comprehensive book called Soil Taxonomy. Okay, you don't have to read that, but I do invite you to look it over if you want to get more detail. Okay, the first thing that we need to talk about when we address soil moisture and temperature regimes, and we're going to use this for other stuff too, is the concept of a control section. A control section is a place in the soil profile where you look for certain features. The second thing that we need to think about for moisture is, what is moisture? Okay, it is designated as dry when it's drier than the permanent wilting point at 1500 kilopascals. How long is the soil moisture dry? That's another thing that'll come into play in determining what the soil moisture regimes are. And also, is the temperature warm enough for biological activity? Okay, so I'm going to click over to the next drawing, and I'm going to try something to enable my animations from the current slide. So one of the first things that we have to do is we have to look at soil moisture control sections which have an upper boundary and a lower boundary. And the upper boundary is the depth to which water will move down. 2.5 centimeters of water will move down after 24 hours. The lower boundary is the depth to which 7.5 centimeters of water will travel after 48 hours. And so this interval between the 24-hour 2.5 centimeters and the 48-hour 7.5 centimeters is called the soil moisture control section. Okay, now for sandy soils, I think you can imagine that water would go more deeply at 24 and 48 hours. And so for sandy textured soils, their soil moisture control section typically will be between about 30 and 90 centimeters. For more moderate, not so fine, not so coarse, but coarse loamy particle size classes, your soil moisture control section will be between 20 and 60 centimeters. And then for very fine textured soils like fine loamy, coarse silty, fine silty, or clayey, the soil moisture control section will be between 20 and 30 centimeters. Now what I've done is I've sneaked in a little bit of a different terminology for you. What's the difference between texture and particle size class? There is a difference between texture and particle size class. Texture is morphological, and this is represented by our soil textural triangle. Particle size class is something that is going to come into play for soil taxonomy. And what I've done is I've superimposed some of the particle size classes on top of the soil textural triangle. So you can see here, this is fine, very fine or clayey. This is finer clayey. We have a sandy particle size class down here, and so forth. We're going to cover this later, and this stuff will be used in soil taxonomy at the family level. So just getting back to where we introduced it, these terms that I was using right here, like coarse loamy and fine loamy, strictly speaking, are particle size classes, not textural types, but you could see that there was a relationship with the soil textural triangle. Okay, hopefully I haven't confused you too much, but we will come back and revisit that. So here's some of the soil moisture stuff summarized. The concept is that you look at cumulative and consecutive periods of dryness and moistness in the soil moisture control section. Dry is water potential less than 1500 kilopascals. Moist means a water potential greater than that, minus 1500 kilopascals. We have soil moisture control sections with rules of thumb or estimates. There's an upper boundary, there's a lower boundary. For sandy textures, it's between 30 and 90. For coarse loamies, it's 20 and 60. For other textures, it's between 10 and 30. Okay, now we actually get down to the soil moisture regimes themselves. Now that we know what moist and dry means, and we know where we're looking at them in the soil profile. So the aeritic moisture regime is in arid climates. It's usually very dry. Irrigation is usually required for crop production. And the main thing here is that the soil moisture control section is dry more than half of the time that the temperatures are high enough for biological activities. The the ustic moisture regimes are semi-arid. You do have some rainfall, like in thunderstorms during the growing season. And the soil moisture control section is moist half to 3/4 of the time, or moist 90 consecutive days. Soil moisture control sections are dry less than 45 consecutive days in the summer. So ustic is a little moister than aeritic. Then we get to xeric, and xeric is very familiar to Californians because it's a Mediterranean climate. It's a semi-arid climate as well, cool moist winters and dry summers. And the difference here is that the soil moisture control section is moist half to 3/4 of the time for more than 45 consecutive days in the winter, but it's dry for more than 45 consecutive days in the summer, and that's where it differs from ustic. Ustic is dry less than 45 days, xeric is dry more than 45 consecutive days in the summer. A moister one still is Utic. Utic is in a humid climate. Soil moisture control section is dry less than 90 cumulative days and less than 45 consecutive days in summer. So it's pretty moist. Generally irrigation not required for crop production. I'm going to skip Utic. Aquic is when soil is saturated long enough to cause anaerobic conditions, and it's not used as a criteria for differentiating taxa. Aquic, how long it needs to be saturated has always been debated, and that will continue to be debated. But under aquic conditions, you would expect to see redoxomorphic features. You would expect to see reduction of iron and manganese, And there are different kinds of saturation conditions that we'll talk about. Anthracite saturation would probably come about because of irrigation. Episaturation is when you have a little bit of a perched water table, and endosaturation is where it's saturated throughout. Okay, let's look at these soil moisture regimes in a graphical form. So the blue areas, this is a pretty coarse picture of the lower 48. The blue areas here indicate aquic moisture regimes. In Florida and the southeastern coastal plain, along the Mississippi River in the Red River Valley, and scattered around the Great Lakes. Also the Sacramento Delta area and some areas of eastern Oregon show up as aquic. Okay, that's the wettest one. The next wettest one is Utic. That's where there really isn't any limitation to soil moisture for plant growth, but it's not waterlogged. There's still probably some pretty good aeration here. And then in the middle we have ustic. Here's an ustic, and here's an intergrade to a Utic ustic, and here's an intergrade to an aritic ustic. So there's different shades of meaning here. So the ustic one is characterized by summer thunderstorms. This is in the Great Plains area, right here. The next one is this orange color, which represents xeric. Xeric is the classic Mediterranean moisture regime, cool, moist winters, hot, dry summers. And you also have some xeric aritic throughout the Intermountain West, and some xeric over here in Idaho and down into parts of Utah. Finally, we have typic aritic, which is the yellow areas. These are true aritic soils, and there are some intergrades to aritic scattered throughout here as well. Now you can use this map to get a rough idea of the soil moisture regime that you're dealing with, but do notice that for a particular pedon, depending on aspect or groundwater reaching the surface or different kinds of slope shapes, you may have very different moisture regimes locally defined. Another way of looking at soil moisture regimes is to evaluate some data to look at whether the soil is moist or dry along with soil temperatures in a tabular format. So in this first table, we have soil temperatures all well above 5 or 8 degrees C, so there can be biological activity here. And it's implied here that the soil moisture control section is dry only in August and September. That would be about 60 days. What do you think the soil moisture regime is as depicted here? This second chart might be a little bit easier. You have dry soil profile, soil moisture control sections from February all the way out to November. Let's look at the next slide for the answers. So this one represents a xeric moisture regime where it's dry greater than 45 consecutive days in the summer, but it's moist more than 45 consecutive days in the winter. And this one is aritic. Sometimes we'll use the term toric for this as well. It's not moist for 90 consecutive days when the temperature is above 8 degrees C. So that's an introduction to tabular format in looking at soil moisture regimes. The other way that you can really understand soil moisture regimes is to look at water balances. So along the x-axis here you have January through December, and then along this axis you have precipitation and evapotranspiration. This diagram is from St. Petersburg, Russia, and there's a water surplus in here. You can see this cross-hatching and the legend over here. There's a water surplus here. There is some water utilization here, a little bit of deficit, and then water recharge as you get into the later months. So this is probably, I'm guessing that this one is Utic. And this picture and similar information is found in Soil Taxonomy, that link that I gave you earlier. And we practiced with these in Soil 260 a little bit. Okay, that's it for soil moisture regimes for right now. Let's move on to soil temperature regimes. And hopefully they are a little bit simpler. Okay? Temperature class names are used as part of the family name unless it's implied elsewhere. And I'm just going to skip down here and say that it's simpler in the sense that the control section for soil temperature either is at a depth of 50 centimeters from the soil surface or it's at the upper boundary of a root-limiting layer, whichever is shallower. Okay, so you look for soil temperature data at about 50 centimeters, and now that's the control section, even though it's only a point. Now let's go on and look at the actual soil temperature classes. Gelisols have some special soil temperature classes, hypergelic, pergelic, and subgelic, but the ones that we're mainly going to be considering that are most important for us are frigid, mesic, thermic, and hyperthermic. Now this middle section assumes that the difference between mean summer soil temperatures and mean winter soil temperatures is greater than 6 degrees C. So given that, if the soil temperatures are lower than 8 degrees, it would be frigid or cryic. We're going to talk about cryic momentarily. If the soil temperatures at the soil temperature control section is between 8 and 15, it would be mesic. Between 15 and 22, thermic, and greater than 22 degrees C would be hyperthermic. Now, if those summer and winter temperatures, soil temperatures, don't differ by more than 6 degrees C, you would add this prefix of iso. So isofrigid, isomesic, and isothermic, and isohyperthermic here. So it's kind of weird, but here on the north coast of California, we actually have an isomesic temperature regime, which is a little bit unusual. Our soil temperatures do not vary very much between summer and winter. Just stays the same temperature all year round. Now, there's another temperature regime called cryic, and cryic is kind of like frigid because it has a mean annual temperature lower than 8 degrees C, but it doesn't have permafrost. Now, the big message here is that cryic is cooler than frigid in the summertime. Cryic is cooler than frigid in the summertime. And this chart here tells you how much cooler it has to be, or how cool it has to be in the summer compared to frigid. And this depends on whether the soil is saturated. So if it's not saturated and if there's no O horizon, a cryic would be lower than 15 degrees C in the summer. If it were frigid, it would probably be higher than that. If there is an O horizon, it would be lower than 8 degrees C. So the O horizon kind of insulates these kinds of soils, which are found up in the mountains and stuff. And then saturation with water insulates it even more. It would keep it cooler if it were saturated. So a cryic, if there's no O horizon and it's saturated, would be less than 13 degrees C. A cryic, if it's saturated and there's an O horizon or a histic epipeton, would have to be lower than 6 degrees C. Okay, so again, the main message here is that cryic is cooler than frigid in the summertime, and that is variable according to whether the soil has an O horizon or not, and whether it's saturated or not, because those two things will insulate the soil from temperature fluctuations. Okay, you made it through a discussion of soil moisture regimes and soil temperature regimes with a little bit of particle size class thrown in there as well. So again, I want to remind you why they're important. Look at this UD right here at the suborder level. Oftentimes, for example, in alpha sols, mollisols, and ultisols, we use soil moisture regime, this would be UDIC, as a differentiating characteristic at the suborder level. If we look at the family level, it's very common to have the soil temperature regime included right here in this position in the family name. And likewise, your particle size classes come in right here, and we'll have to talk about those later. So thank you for listening. I hope you have a great weekend, and don't forget to take your reading quiz before about 11:55 p.m. on the night of Monday, September 7th. Any time before that will be good. Okay, we'll talk to you later.